reference formulas for sine, cosine, and tangent. If I give you two angles, alpha and beta, let's say, then I can come up with formulas for the sine of alpha plus beta or alpha minus beta, and same thing for cosine and tangent. Proving these is beyond our course, and we will not discuss that. The other thing I will point out is if you look in a textbook, you will typically see these written with alpha and beta, but also some textbooks might use U and V. Some other textbooks might use something else. If you on your own paper say A and B as opposed to alpha and beta, that's also fine. That's not a detail I'm concerned with. So the sine of alpha plus beta will be the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Now, the cosine of alpha plus beta is the cosine of alpha times the cosine of beta, and weirdly, up here we see plus and over here we see subtraction. Cos alpha, cos beta minus sine alpha, sine beta. For tangent, we see the tangent of alpha plus beta is tan alpha plus tan beta over 1 minus tan alpha, tan beta. If you're looking at those signs, you notice that up on top the sign matches the plus, in the denominator the sign is the opposite. Well, that also makes sense if you think about tangent is sine over cosine, so it would make sense that it's the same sign up on top and the opposite sign in the denominator. There's a little more to it than that, but again, we don't need to obsess over that detail. What happens if I instead do a difference? What if I do sine or cosine or tangent of alpha minus beta? Well, for the sine of alpha minus beta, I will have sine alpha cos beta, but now it will be minus cos alpha sine beta. For the cosine of alpha minus beta, well, I will have cos alpha cos beta, and again, the sign will be opposite because it is cosine. I see plus in here, sine alpha sine beta. For the tangent of alpha minus beta, again, on the top I'll see the same sign, and in the bottom I see the opposite sign. Tan alpha minus tan beta over 1 plus tangent alpha tangent beta. And again, why those two work, why the tangent formulas work the way they do, can be derived using only the sine and cosine. It's a bit of an interesting look, but it's not something I'm going to do right now. All right, so here's the idea. These formulas work regardless of what two angles you may be considering. If they're angles on the unit circle, that's great. If there's some random angles for which you need to draw reference triangles, these will also work, and that will also be something that you have to learn for this lesson. But they will also work for just other totally random angles, like if I had a 10-degree angle and a 50-degree angle. Well, 10 plus 50 is 60, so from that I could derive additional information. Let's take a look at some examples. If I asked you for the sine of 210 degrees, well, 210 degrees we know is on our unit circle, so we should already be able to figure out the sine of 210 degrees. I would note, though, that 210 is actually 180 plus 30. So I should be able to use the sum formula up above and say that this is, in fact, the sine of 180 degrees times the cosine of 30 degrees plus the cosine of 180 degrees times the sine of 30 degrees. And again, we already know those things. The sine of 180 degrees is simply 0. The cosine of 30 degrees is root 3 over 2. The cosine of 180 degrees is negative 1, and the sine of 30 degrees is 1/2. So what do we see? We get an end result of negative 1/2. And if you check your unit circle, you will confirm that, again, that is actually the sine of 210 degrees, negative 1/2. What if we did this with a tangent? So, for example, the tangent of pi over 3. Pi over 3 is pi over 6 plus pi over 6. So if I use my tangent sum formula, this is the tangent of pi over 6 plus the tangent of pi over 6, and again, I'm just looking at the formula right here, over 1 minus the tangent of pi over 6 times the tangent of pi over 6. Okay? Well, tangent of pi over 6, we might recall, is the square root of 3 over 3. So let's take a look at how this plays out. Square root of 3 over 3 plus square root of 3 over 3 over 1 minus the square root of 3 over 3 times itself. Okay? So, I can do some work here. Up on top, I have 2 square root 3 over 3. In the denominator, I have 1 minus 3/9, which is 1/3. So since this is 1/3, what I really have down there is 1 minus 1/3, or 2/3. So what I'm actually looking at right here is 2 root 3 over 3 over 2/3. Now again, I'm going to pause for a second here and remind you, what I'm trying to show you is that this formula does work. We're trying to show that, that this produces the tangent of pi over 3, which is a value that we know. So let's just take a closer look. Let's continue on. The quotient of 2 fractions can be rewritten as a multiplication problem. And if I do that, I can simplify the 3's, I can simplify the 2's, and I get simply the square root of 3, which hopefully we can recall that that is indeed the tangent of pi over 3, or 60 degrees. All right. Now, these are things that we already knew. What if I gave you something, an angle that was unfamiliar? Take a look at these examples right here. The cosine of 170 degrees times the cosine of 35 degrees plus the sine of 170 degrees times the sine of 35 degrees. Now this probably looks like a lot of gobbledygook the first time you see it, but we want to train ourselves to understand what's going on here. What am I actually looking at? Well, I see cos times cos and sine times sine. So this is telling me this is some sort of cosine sum or difference formula. Is it a sum or is it a difference? Well, I remember right here there's a plus, and cosine's abnormal. That plus actually means what I want to do is subtract. So this is actually the cosine of the difference, 170 minus 35 degrees. Well, 170 minus 35 is 135 degrees. And again, I know that's a 45-degree reference angle. I'm in the second quadrant. So the cosine there is negative square root 2 over 2. So again, this reinforces things that we already know as part of what it can do. Take a look at the one beside it. I see the tangent of 307 degrees plus the tangent of 188 degrees over 1 minus tan 307 times tan 188. Again, these numbers seem random. They're certainly not very pleasing to look at, but I can recognize that this is tangent sum. I know that this is the tangent sum formula. So I'm going to recognize this and say that, oh, this must actually be the tangent of 307 degrees plus 188 degrees. Well, 307 plus 188 is 495 degrees. Well, 495 degrees is larger than 360. This is coterminal to 135 degrees. So again, I'm thinking about a 45-degree reference angle in the second quadrant, just as I did in the last problem. And I have to remind myself that 45-degree reference angles, the tangent's either 1 or negative 1. And in the second quadrant, with 135 degrees, it is, in fact, negative 1. Okay. So, what I'm showing you is these formulas do work. They work with things that we already know. They may help us to simplify some expressions that, aren't particularly pretty. We don't know the exact value of the sine of 35 or cosine of 170 or the tangent of 307 or any of those things. But these expressions in concert come out to things that we do know. Right? Now, what if we tried to go in the opposite direction? What if I needed to go the other way? This is something you can expect to be asked. This will be one of the bulk of your work, one of the two main problem types that you can expect to see. I can also use these formulas to find trig values we did not previously know, exact trig values. Specifically, we can break our angles down further rather than going in increments of 30 and 45. We can actually break this down further and go to increments of 15 degrees. So 15 degrees from the axes, I would find myself at either 15 degrees or 75 degrees or 105 degrees if I'm 15 degrees away from the y-axis. 165 is 15 degrees away from the the negative x-axis. In radians, these are all some form of pi over 12, whether that's pi over 12 or 5 pi over 12 or 7 pi over 12, etc. We want to see how to use these things. All right, so this first example, I am asked to compute the cosine of 15 degrees. Well, what is the significance of 15 degrees? I know that 15 degrees is 45 minus 30. It is also 60 minus 45. Either of those would be an acceptable way to get to the answer that I want. But what I'm definitely going to do is use the cosine of a difference. I'm going to use cos alpha minus beta. As I said, I can do 45 minus 30, or I can do 60 minus 45. Either one will work. I am going to choose randomly to just do 45 minus 30. So cosine 45, cosine 30, plus, because I'm remembering my cosine my cosine difference formula, sine 45, sine 30. What does this come out to be? Well, the cosine of 45 degrees is the square root of 2 over 2. The cosine of 30 degrees is root 3 over 2. How about the sine of 45 degrees? That is also root 2 over 2. And the sine of 30 degrees will be simply 1/2. Now, when I do this, typically I'm not going to look to simplify, although in most instances it's not super likely to see something that simplifies, which is to say simplify between the numerator and denominator. I'm just going to multiply these together, and you'll see I have a common denominator. Each of these will be over 4. So what I can do is say that, oh, this is the square root of 6 plus the square root of 2 over 4. And then I got a nice, fairly simple looking answer. Right? Now, if you're given this in degrees, it's relatively simple to figure out what angles to use most of the time. It can be a bit trickier if you are given radians, although my advice to you will be to try to not overthink this. I want 13 pi over 12 in the next example, 13 pi 12ths. So how I want to think about doing this? 13 pi over 12 could be expressed in a number of different ways. It's 1 pi over 12 plus 12 pi over 12. It's 2 pi over 12 plus 11 pi over 12. And I could keep going on in this fashion. Here is the trick. I really want to express these in terms of angles that I know from my unit circle. So what I will be doing is looking for things that in one way or another simplify. So basically I want to express 13 as a sum of two numbers. One of them wants to be a multiple of 3, one of them wants to be a multiple of 4. Okay? So if I go ahead thinking like that, what did we say 13 was? It's 1 and 12. Well, there's a multiple of 4 and 3, but then I got 1. That doesn't really help me. It's also 2 and 11. That doesn't really help me either. It's 3 and 10. No such luck there. It is, however, 4 and 9. So if I think of 13 pi over 12 as 4 pi over 12 plus 9 pi over 12, then I can understand this as, oh, 4 pi over 12 is pi over 3. 9 pi over 12 is 3 pi over 4. And now these are values from the unit circle that I actually know. Okay? So, let's go ahead and get our formula. We know that this is going to be this, the sine of pi over 3 plus 3 pi over 4. Our sine sum formula will be sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. Okay? And if I do this, it should work out exactly the way I want it to. The sine of pi over 3 is root 3 over 2. The cosine of 3 pi over 4 is negative root 2 over 2. The cosine of pi over 3 is 1/2, and the sine of 3 pi over 4 is root 2 over 2. So if I look at this, I'm going to see something that looks pretty darn similar to the answer I just got previously, except it is now negative square root 6 plus the square root of 2, still over 4. Okay? That's what I have. That is, in fact, my answer. Now, you can think about this in a lot of ways. This does logically make sense. If you think about negative square root 6 plus square root 2, this is indeed a negative number. Well, 13 pi over 12 is in the third quadrant. It's just past a full pi, which means it makes sense that the sign would, in fact, be negative. So this answer makes sense. And in all honesty, if you do enough of these, you're going to pretty much keep seeing variations on square root of 6 plus 2 or square root of 6 minus square root of 2, similar things to that. Now the exception will be if we do a tangent. Let's do a tangent example next. So I see 19 pi over 12. And again, there's multiple ways I could come at this. 19 pi over 12. I could try and do this via subtraction. I could try and do this via addition. For me, addition makes the most sense. I see 19 and I think of 16 twelfths plus 3 twelfths. Are there other possibilities? Well, if you worked your way through it, you would also have 1 and 18, 2 and 17, 3 and 16 I just came up with. 4 and 15 would also work. 4 pi over 12 and 15 pi over 12. These both work. So there are multiple ways to do this same problem. Just have to pick one because they should all produce the same answer. I'm going to go ahead and do this. I'm going to say that this is the tangent of 16 pi over 12 is 4 pi over 3. And 3 pi over 12 is pi over 4. Now my tangent formula is a little bit more complicated. There's a little more going on here. So I will have the tangent of 4 pi over 3 plus the tangent of pi over 4 over 1 minus, and I want the product of those two tangents. So the tangent of 4 pi over 3 times the tangent of pi over 4. I'm going to work through this very carefully. The tangent of 4 pi over 3. So that is a 60-degree reference angle in the fourth quadrant. So that will be the square root of 3. The tangent of pi over 4 is 1. Okay. Down below, I will have 1 minus the square root of 3 times 1. Okay? So I get this answer right here, the square root of 3 plus 1 over 1 minus the square root of 3. Now that's pretty close to the final answer that we want. But as we do more of these, you're going to see more problems like this, where this denominator needs to be rationalized, meaning I do not want to leave a radical in that denominator. I want to change this. Now, how do I do that? Well, you rationalize something like this. You rationalize a sum or difference by multiplying by what is called the conjugate. Okay? So I take 1 minus the square root of 3, and I'm going to multiply by its conjugate. Same expression, but I change the operation in between. You have to multiply these things out carefully. It takes a bit of work. You have to FOIL or what have you. In the denominator, the whole idea is this is, if you look at it, is a factorization like a difference of squares. So what I end up getting is just 1 minus 3. In the numerator, I have to work out a little bit more. I can FOIL it. I will have square root of 3 plus 3 plus 1. Let me write this down. Square root of 3 plus 1 plus the square root of 3, also known as 4 plus 2 square root 3. Now this denominator is actually negative 2. So what I can do is divide and give a final answer that's still a little bit neater. -2 minus the square root of 3. Now, if that rationalizing is the trickiest part of this, that's okay. There's a large part of that I would say is to be expected. Focus on getting here. If you can get to here, if you can get to the simplified version, that's a good place to be. This will be something, again, that we practice more as we move forward, and as we see it more, I assure you it will make more sense, and you'll gain more facility. Now, there's one more example here. That's 5 pi over 12. 5/12 is a little bit trickier. I think the only way you can get 5/12 is by subtraction. So you might try something like 6 minus 1, which clearly doesn't work, or 7 minus 2, which also doesn't work. Keep going from there. Eventually you will find something like one of these, where you have a multiple of 4 and a multiple of 3, which leads us to nice math.